And this brings us to our last topic, partial differential equations. Right. Throughout this course, we have been studying ordinary differential equations. For example, ODEs are the ones with the total derivative. So dy by dx plus sine of x y equals x square. So that's a total derivative. Y double prime minus 7y prime plus 12y equals, let's say, x cubed minus x square. Again, it involves total derivatives. So there is only one dependent variable and one independent variable. Y is a function of x only. So that's why the resulting differential equation is an ordinary differential equation, because the derivative of y with respect to x is a total derivative. What if we have a function which is more than one variable? Let's say if u is a function of x and t, then in that case, when we write an equation involving u and x, let's say partial to u by partial x, a square partial to u by partial t equals x square. This one is called a partial differential equation because it involves partial derivatives of u with respect to x and t. There are different methods to solve partial differential equations, but we will only do one basic method, and we will start with a very famous equation called heat equation, and we will do separation of variables method. So the equation is k partial 2u by partial x square equals partial u by partial t, where x is between some range 0 and L and t is a positive number. The method we will use is called separation of variables. It's the same method, same name as we used in the very first ordinary differential equations, but of course the method here is different. So here is how it starts. First of all, we consider that our function u, which is a function of x and t, we think of it as two separate multiplied functions. We can use here x, generally we use f and g for functions. We can use f of x and g of t, but traditionally at this point books use capital X for the function of x and capital T for the function of small t. So that's what we will use. So capital X is like f here and capital T is like g here. So they are the functions, and x and t are the variables. Small x and t are the variables. Now we find partial u by partial x, because in this case this will be constant and x only depends on x, so that will be dx by dx, and a t will be as it is. And if we have to do one more time, that will give d2x over dx square. Again, note that our capital X is only function of t. Sometimes we write it as x prime t and this one as x double prime t. And when we differentiate the same thing with respect to t, now x will not change and it will be dt over dt, or sometimes we write it as xt. Let's put these values into the equation, okay, and that gives k times partial 2u by partial x square equals partial u by partial t. So that will become k x double prime t equals xt prime. in order to successfully separate the variables, we divide this expression divide by xt, okay, across. So we get x double prime t over xt, xt prime over xt. That would give k x double prime over x, because t is cancelled here, and t prime over t. As you can see, our x is separated out and x double prime is and t is separated out. Right. Here, what we do, one more step, I'll explain this at another stage, but then we can skip this step, the one I'm going to do now, divide by k. Okay, you can solve it without dividing by k. It will give you the exact same solution, but this is also a matter of culture, more or less, but that makes our life a little bit easier, because when we solve it, k will go up. Okay, once we do the next step, k will go up again, so we won't have a fraction to handle all the way along. And then now we put this expression equals to minus lambda. Once again, we can put it equal to plus lambda or any other constant you want. It will work very good, but minus lambda will make our life a little bit easier. Okay, it's just a mathematical technicality. It makes life a little easier later, so that's why we suppose minus lambda. Otherwise, plus lambda will be equally good. Now from here we make two equations, x double prime over x equals minus lambda, and 1 over k t prime over t equals minus lambda. As you can see, now we have two separate equations, one in x and one in t, and both are ordinary differential equations, because x is only dependent on small x, and t is only dependent on small t. And we can write x double prime plus lambda x equals 0, and t prime plus k lambda t. If I write this in the form which we used to write equations, you can see that we have solved such equations many times in our course, in the first chapter and in the second chapter. This one is linear first order, this one is linear second order, and the solutions are very simple and easy. But there is one little glitch. The solution depends on the value of lambda in this case, not in this case, but in this second order case, the solution depends on the value of lambda, whether it's positive, negative, or 0. So what we will do is, we will give them numbers. So this, let's say this one is number 1 and this one is number 2. I will solve number 2 first. Okay. Number 2 first. So let's solve number 2 first. We can solve it using variable separable form, minus k lambda t, that implies dt over equals minus k lambda dt, and when we integrate, and we get log of t equals minus k lambda t plus c1, and t equals e raised power minus k lambda t plus c1, which is equal to e power minus k lambda t into e power c1, and t of t is let's c2, let's call it c2, minus k lambda t. So that's the solution of our second equation, this one over this one in t here. Now we are going to solve our first equation, which is d2 x over d dx squared plus lambda x equals 0. And we know that we solve these equations using auxiliary equation. If you remember, exercise 3.1 or 3.2. So auxiliary equation we write, which is m square plus lambda equals 0, and that gives m square equals minus lambda. Now we don't know what is lambda here. It's a number. Lambda is some constant. So if lambda, let's say if lambda is 0, then we get the roots 0, 0. And if lambda is positive, then we get imaginary roots. And if lambda is negative, then we get real roots. So it gives rise to 3 cases here. So we will discuss them one by one. So the first case, I'll call it A. If lambda is 0, then m square equals 0, and this implies m equals 0, 0. Never forget to write both roots separately. And in this case, x of x will be, let's not repeat the value of the constant. We have already used c1 and c2, so I'll use c3 plus c4x. Second is if lambda is positive. Okay? In this case, I'll put lambda equals alpha squared just to make our lives easier, and that will give me minus alpha squared. Okay? And that gives m square plus alpha square equals 0, or we can write m equals plus minus alpha iota. Okay? And in this case, we get x of x equals, I'll use 2 new constants again, 5c5 cos alpha x, c6 sine alpha x. Third possibility is if lambda is negative. So what we will do is we put lambda equals minus alpha square or beta square, maybe, just to make it different, minus beta square. So this implies m square equals beta square, or in other words, m equals plus minus beta, real roots, and that gives x of x equals c1 e power beta x, c2 e power minus beta x. So we have 3 answers for this equation, and there is 1 answer for t's equation. Now we are going to put them together. Okay? So our answer was u of xt equals x of x and t of t. So what if, so now we have 3 cases. A, lambda equals 0. In this case, our solution is u of xt equals what were the constants we used for 0? c3 and 4. So from x of x we have c3 plus c4x, and from t of t, from the solution of t of t, here is the solution of t of t. If lambda is 0, this whole thing will become 1, and we will only get c2. Okay? c2. So we'll rename the constants because we don't want to use too many constants. So I'll rename them a1 plus a2x. Okay? Just capital A and capital B. What if lambda is greater than 0? What is our solution in this case? So from x of x we get from c5 cos alpha x, c5 cos alpha x plus c6 sin alpha x. Okay? And from t of t, let's move it a little bit to the left so that to make a little bit more space for our solution. And from t of t we get c2 e raised power minus k lambda t. C2 e raised power minus k lambda t. If you remember, For lambda greater than 0, we had put lambda equals alpha square. Lambda equals alpha square. So we will do the same for t's part. This is equal to, I'll rename the constants first of all, a3 cos alpha x, a4 sine alpha x into e raised power minus k alpha square t. And for lambda less than 0, our solution equals c. I've used 1 and 2 again. No, I should not use 1 and 2 again. I'll use 7 and 8 maybe. C7 e raised power beta x plus C8 e raised power minus beta x e raised power minus C2 e raised power C2 e raised power minus k lambda t. And once again, we will rename the constants first. A5 e raised power beta x plus a6 e raised power minus beta x into bracket here c e raised power minus k beta square t minus beta square, so this will go away. And that completes our solution of the PDE for now.